Have you ever wondered what the future of computing might look like? We live in a world where conventional computers are reaching their limits, with silicon chips that are smaller than ever, and processing speeds that seem to be reaching a plateau. But what if we told you there's a new horizon in the field of computing, one that promises to blast through these limitations and redefine our understanding of computation? Enter the realm of quantum computing. This isn't just about making our computers faster or storing more data. It's about harnessing the strange and wonderful laws of quantum physics to process information in ways that traditional computers cannot even dream of. It's about solving complex problems in seconds that would take a traditional computer millions of years. As we journey into the future, quantum computing stands as a beacon of potential, ready to redefine our understanding of computation. The inception of quantum computing dates back to the early 1980s. This was a time when the world was just beginning to grasp the potential of classical computers, yet there were visionaries who were already looking beyond. One such visionary was Richard Feynman. Feynman, a renowned physicist, proposed a radical idea. He suggested that instead of trying to simulate quantum mechanics with classical computers, why not create a computer that operates on the principles of quantum mechanics itself? This idea was revolutionary. Quantum mechanics, with its strange phenomena such as superposition and entanglement, was a world apart from the binary logic of classical computers. It was like comparing a biplane to a spaceship. Yet, Feynman's proposal was not without merit. Quantum systems can exist in multiple states simultaneously, potentially allowing a quantum computer to crunch through vast amounts of data at once. It was a tantalizing prospect. However, Feynman's proposal was just the beginning. Theoretical groundwork had to be laid before quantum computing could become a reality. Throughout the 1980s and 1990s, scientists developed the theoretical foundations of quantum computing, including the basic principles of how a quantum computer might work. Then came the development of the first quantum algorithms. Peter Shor, a mathematician at Bell Labs, devised an algorithm that could factor large numbers much more efficiently than any classical computer. This was a big deal. Factoring large numbers is a notoriously difficult problem for classical computers, and it underpins the security of many encryption systems. Shor's algorithm demonstrated that a quantum computer could, in theory, crack these systems wide open. The development of Shor's algorithm and others signaled a turning point. Quantum computing was no longer just a theoretical curiosity. It had the potential to solve real-world problems, problems that were beyond the reach of classical computers. As the 20th century came to a close, quantum computing had transitioned from theory to a budding reality. With the dawn of the new millennium, quantum computing started to gain traction. The early 21st century was a time of unprecedented advancements in this cutting-edge field. Theoretical concepts began to manifest into tangible technology, and the world of computing was poised for a seismic shift. One of the most significant milestones was the development of the first quantum processors. Unlike traditional processors that use bits to process information, quantum processors use quantum bits or qubits. The magic of qubits lies in their ability to exist in multiple states simultaneously, thanks to a quantum quirk called superposition. This means they can process vast amounts of data at speeds that leave conventional computers in the dust. In the early 2000s, technology giants and ambitious startups alike recognized the potential of quantum processing. Companies like D-Wave Systems released their first commercial quantum computers, setting the stage for a new era of high-speed, high-capacity computing. Around the same time, quantum cryptography emerged as a promising new field. Utilizing the principles of quantum mechanics, scientists developed methods to encrypt data in a way that's virtually unhackable. Quantum cryptography leverages another quantum oddity: entanglement. When two particles are entangled, what happens to one instantly affects the other, no matter the distance between them. This phenomenon allows for the creation of cryptographic keys that, if tampered with, would immediately alert the intended recipients. This period was a hotbed of innovation, with researchers around the globe working tirelessly to unlock the potential of quantum technology. But as with any pioneering field, it was not without its trials. Scientists faced, and continue to face, significant challenges in maintaining the stability of qubits and in scaling up quantum systems. These achievements marked significant milestones, but the best was yet to come. Fast forward to today, and quantum computing has reached unprecedented heights. Quantum computing, once a theoretical concept, is now a reality, with tech giants and research institutions worldwide developing quantum computers and algorithms. One of the most notable milestones in this field was achieved by Google in late 2019. They announced a breakthrough that sent ripples through the scientific community: quantum supremacy. This means they developed a quantum computer that could solve a problem no classical computer could realistically tackle in a reasonable time frame. This feat was performed by their 53-qubit quantum processor named Sycamore, which completed a task in just 200 seconds that would take the world's most powerful supercomputer approximately 10,000 years. But it's not just about speed. Quantum computers can process a vast number of possibilities at once, opening up new avenues in fields such as cryptography, material science, and drug discovery. Yet, this immense power comes with a set of unique challenges. Qubits, the fundamental units of quantum information, are incredibly fragile and easily disturbed by their environment. This leads to errors in computation, a problem that scientists are tirelessly working to overcome. A promising solution to this problem lies in the development of error-corrected quantum computers. Researchers are exploring techniques for detecting and correcting errors in quantum computation, a crucial step towards building reliable and practical quantum systems. This development could significantly enhance the stability and reliability of quantum computers, bringing us closer to realizing their full potential. The strides made in quantum computing are truly remarkable, representing the culmination of decades of research and innovation. Yet, we must remember that we are still in the early days of this technology. There is much we have yet to learn about the quantum realm and its potential to revolutionize computation. As we stand on the cusp of a new era, we can only imagine what the future holds for quantum computing. So what does the future hold for quantum computing? As we cast our gaze forward, we find a horizon teeming with potential. The potential applications of quantum computing are vast and varied, promising to revolutionize fields from drug discovery to climate modeling and even cryptography. Imagine a future where we can accurately model and predict the impacts of climate change. Quantum computers, with their ability to handle complex calculations at speeds far beyond the reach of traditional computers, could be pivotal in creating detailed and precise climate models. This could empower us to make more informed decisions about our planet's health and our own survival. In the realm of drug discovery, quantum computing could be a game changer. The ability to simulate and analyze molecular interactions at an unprecedented scale could significantly speed up the development of new drugs and treatments. This could potentially save countless lives and improve the quality of life for many more. Looking at cryptography, the very foundation of our digital security could be transformed. Quantum computers could crack codes that would take conventional computers millennia to solve. But on the flip side, they can also create unbreakable encryption, ushering in a new era of cybersecurity. However, the road to this future is not without its challenges. Quantum error correction, a process that corrects the errors that occur during quantum computations, is one of the key hurdles we need to overcome. Additionally, the issue of quantum decoherence, where quantum states lose their quantum behavior over time, also needs to be addressed. These challenges are significant, but they are not insurmountable. Scientists around the world are tirelessly working on solutions, and every day brings us closer to a breakthrough. As we continue to push the boundaries of what's possible, the future of quantum computing looks brighter than ever. The promise of quantum computing is not just about faster computations, but about unlocking new ways of understanding our world, and possibly even ourselves. The quantum future is full of promise, and it's a future we're building today. So, we've taken a journey from the inception of quantum computing to its potential future. We've seen how this exciting field has evolved over time, from the early days of theoretical concepts to the tangible advancements we're seeing today. We dove into the nitty-gritty of qubits, superposition, and entanglement, demystifying these complex aspects of quantum computing. We've also explored the current state of quantum computing, looking at how it's being used and the challenges faced in making it more accessible and practical. We've discussed the enormous potential of quantum computing, from revolutionizing data encryption to transforming drug discovery and climate modeling. And finally, we've peeked into the future, contemplating the promise and the hurdles of quantum computing. From increasing computational power exponentially to overcoming decoherence, we've seen that the journey is as much about the challenges as it is about the breakthroughs. As we step into the future, one thing is certain: the world of computing will never be the same again.